one of the most important things to understand about quantum computing is it's not going to replace the things or the workloads that we're doing in classical computing. It's going to open up whole new workloads. And so I don't see this as necessarily a disruptor to GPUs or classical computing at large. It will be an expansion of what humanity can throw compute at. Let's call it that. So the vision of the future data center that I have is just like GPUs layered in on top of CPUs to enable new use cases. You're going to have quantum processor units, or QPUs, sit above those, and workloads will get sent into the data center in the cloud, and they'll be chopped up, and the parts that the various parts of the stack are best suited to solve, the workloads will be sent to those parts. And so the underlying infrastructure to do that is something that we focused a lot on, and we focused a lot on it with NVIDIA. NVIDIA is really taking a leadership position in that bridge between quantum and classical. And so they announced something called NVQ Link in October of this year, which is really exactly that. It is the bridge to allow workloads to pass really seamlessly between quantum computers and classical GPU clusters. And a good example of how that might look in the future is something we did with them just about a year ago, where we solved a very basic material science problem called the Anderson impurity model. It's a photovoltaic model. Parts of it were solved on a GPU cluster, but parts of it that wouldn't have been able to be solved by GPUs were solved on our quantum computer. And then they recombined to give the answer. And we talked a lot about how, nature does quantum better than anyone. Quantum is really the computational method of nature. And so the types of problems that quantum computers are going to be very good at solving are those that are really rooted in nature themselves. And so the ability to model the interactions of electrons when you're combining different molecules, that's inherently quantum mechanical in nature. And even the most powerful GPU cluster at the end of the day is boiling everything down to zeros and ones, right? And that's not how nature fundamentally works. And so these types of nature-based problems break on classical computers because they can't be boiled down to that heuristic of 0 or 1. And so a lot of the parts of that Anderson impurity model could be, solved by the classical computer. So it was the combination of the two that was what made us able to do something that had never been done before. I think you can think about that as a very not commercially useful example yet, but you expand that over time, and that's how we're going to build better batteries. So your iPhone having to be charged every night, you could build a battery that lasts for a year maybe, right? Or much longer, or help solve the Haber-Bosch process, which is what we use to build fertilizer. And we've been trying for 100 years to find a better catalyst, but it's just too complex to model that interaction. That's the type of thing that quantum computers will be able to do in tandem with classical computers.
Is it fair to think about classical computing as a bit of a brute force modality, and then quantum as more of a finesse driven modality?
It's not a bad way to think about it. You are boiling all of life's problems down to Boolean 0 or 1 logic, and what we can do by boiling life's problems down to that type of logic is incredible, right? It's amazing what you can do with doing that 0 or 1 billions of times, but that's not fundamentally how nature works. And so, yes, we're kind of brute forcing these problems. And that's why I think you see the power consumption issues when we're starting to throw classical computing at problems that it maybe wasn't well suited to solve.
Could you speak a bit about the algorithms or the software that you're running on those as well?
I do think software isn't talked enough about in quantum computing. Even at the most basic level, we're shooting atoms at lasers, but it's not like I'm sitting there with a laser gun shooting the atoms. We are programming these lasers with software to do this at very, very precise, literally atomic level precision. When you write software, and going back to software for quantum computers, you have to write it in a fundamentally different way, because you actually have to code around some of the laws of quantum mechanics. And one of those laws is called the no cloning theorem, which is very interesting. You can't copy and paste quantum data, which copying and pasting data is like, it's all over the place in classical software, right? And so when we write our software for our quantum computers, we write this kind of very different software that doesn't do some of the things that would be very natural to do in classical software development. And that means we have to sort of re-architect the memory. But what we did was we started to run this re-architected memory software on GPUs. And it turns out that actually provides some very interesting performance enhancements to GPUs, largely around the enlargement of the context window, which is one of the fundamental scaling bottlenecks to GPUs. And that's because the memory is totally re-architected. It's quantum in nature. And so we've kind of been trying to bridge the gap between classical computing and quantum computing hardware by software, and giving some of that quantum advantage to classical computing kind of via software, and rewinding or bringing forward the time to quantum advantage by software. So that's a kind of really interesting bridge we've been working on.
That's really cool. You'll have to keep us posted there. That's really interesting.
We just announced a really cool contract with the Army. It's called Sapient Secure AI for PNT. What they're and this is based on our what we call contextual machine learning software. So it is our contextual machine learning software running on edge GPUs, like NVIDIA's Jetson, so small GPUs that don't have a ton of power or memory on them, and allowing them to ingest far more streaming data. So think of like video data, speed data, inertial motion data, and process all of that multimodal sensor data right there on the edge, which would have normally overwhelmed the memory capabilities of that GPU. But this allows them to expand it and then recreate some of the basic things that GPS is giving you, like where you are in the world, by extrapolating by all the different external signals that can be brought in onto this GPU. And so that's where the name Secure AI for PNT comes from. And so that's a kind of very interesting near-term use case that we're working with the Army on. But yeah, it wouldn't be possible without this software.